All right, I think we can get going. We have a good amount of people already in the call. If anyone else joins late, they can just fill in. Welcome everyone to today's webinar. With me on the call, we have Michael Schmid, Head Technology at amazee.io, and Bastian Wittmer, Systems Engineer at amazee.io, leading us through today's webinar called Kubernetes 102, a deeper dive into Kubernetes. This forms part 2 in our webinar series. If you have missed the first installment, you can grab a recording of that on our blog as well as our YouTube channel. Before we get going, we have a little bit of housekeeping to do. Just letting you know that we will run several short sectional Q&As throughout the webinar, meaning we will interrupt for short bits, allowing everyone to ask questions throughout the webinar, but also dedicate some extra time to a full functional Q&A session at the very end of it. You can ask questions throughout all of those sessions by using the center panel of your Zoom window titled Q&A, and we'll attend those questions in the respective Q&A session. All right, without any further ado, I'm opening up the floor for today's speaker. Over to you, Michael.
Hello. Yes, thanks, Philip, for that introduction. And welcome to our second webinar around Kubernetes. We learned in the first one that we did a couple of weeks ago, we learned mostly what Kubernetes is, why it exists, why do we even need containers and orchestrators, and today we want to look a bit deeper. But just a first short intro into who we are, what we do. So we are amazee.io. We are a fully managed cloud and dedicated container hosting company, and we're using Lagoon for that, and of course a lot of Kubernetes. We can host anywhere in the world. Kubernetes can run pretty much in any data center, so can we. We do support via chat, and everything we do is open source. Not only the tools we use, but also everything we build ourselves is open sourced on our GitHub, and we welcome everybody to look into it, find bugs, or send us improvements. As we say, we do managed hosting. This means we have customers like governments, financial services, universities, and others that we do and host for. So for today, we have 3 main topics. First of all, we want to talk a bit about managed Kubernetes. Then we want to talk about how do we deploy into Kubernetes, what are the different ways how to get your applications in a Kubernetes cluster. And then we also want to talk about actually Kubernetes in production. So let's jump right in. Let's talk about managed Kubernetes. Last time we talked about, or in the 101, we heard about self-managed Kubernetes, which means that, like in the example on the right side here, we have 3 master nodes and we have 3 compute nodes. This means if you are running that cluster, you need to manage these 3 masters, and you need to also manage these 3 nodes. And if we talk about management, this means you have full responsibility about things like the actual configurations of these servers, or if you use virtual machines, you need to size them, you need to set them up, you need to configure them, and you need to set up networking in between them. You might have these servers span across multiple regions or data centers, so you need to make sure they can talk to each other. You need to set up an operating system on each of them. And then you need to set up Kubernetes inside of these VMs. Then you need to worry about security. You need to make sure that the nodes and the servers cannot be accessed from the internet without proper boundaries and firewall rules and stuff like that. Plus, if everything is running, you need to upgrade the operating systems. Operating systems usually have new releases every week, so you need to make sure. And then Kubernetes itself has also updates, so you need to do them as well. And then you probably want to know what is going on. So you need to install a monitoring and logging system, and maybe even an alerting system. And of course, you also need to think about the backups. So what happens if some of these nodes are dying, or if an application has a problem? How do you restore backups and that stuff? So there's a lot of things that if you want to run your own Kubernetes clusters and you want to run it self-managed, that you need to think about, you need to worry about, you need to be up to, and work on it. On the other side, as you probably know, there is a lot of talk today about managed Kubernetes. And basically a managed Kubernetes means that the control plane, or these masters also called, you get them as a service. That means the masters are basically managed by a cloud provider. And you, as a user of that Kubernetes or managed Kubernetes, you just talk to an API endpoint. Kubernetes is all built around APIs, so you just talk to an API and you don't actually see how many masters or how is that control plane built. All you do is you talk to an API endpoint, and the cloud provider manages that masters for you. Important to note, though, is that because they manage it, they only provide specific versions of Kubernetes. So that can be an issue with if you want to stay on a specific version, and they might actually force you to upgrade. So of course, because they take over some responsibility for you, you need to think about what that all means. And usually it is cheaper than a self-managed Kubernetes because you actually only run these nodes, while the masters themselves, the VMs, you don't pay anymore. Some providers still charge you a little bit, others make it completely free. It depends a bit, but overall, it's probably cheaper to do this. But if we look at the responsibilities, we can see that you don't need to manage the masters anymore, which is already a good thing. But we still need to do the management of the nodes. So this means we still have some partial responsibility. We still need to set up these servers. Now, that being said, a lot of managed Kubernetes systems have good sane defaults. So you can just tell the Kubernetes, hey, start me 3 nodes, and they will start in a good configuration. But you maybe still want to check, how are these VMs configured? The same for the networking. A lot of managed Kubernetes systems come with predefined networking, but again, check what it's actually doing. The operating system usually also comes with the servers already, but maybe also make sure that it's configured correctly. The Kubernetes usually is all there. You don't have to do anything, but still check what it does. Security, again, a lot of the managed Kubernetes systems have really good sane defaults, but make sure that it's all there. Operating system upgrades are still required, especially on the nodes. On the masters, they are done by the managers, so the cloud provider, but on the nodes themselves, you still need to do them. Or you just start new nodes with the newest version and you stop the old nodes, that's also possible. And then Kubernetes upgrades, which are mostly happening inside the masters, but your nodes still need to also be upgraded. So it's still something that you need to trigger while the actual upgrade then happens fully automatically. But you still have full responsibility around all of it about the monitoring and the logging environment. So anything there that you would like to have is still necessary. There are some cloud providers that inside the managed Kubernetes, you can just enable monitoring, but you still want to make sure that you get informed when something goes wrong inside, and mostly around backups. And it's not something that is automatically solved by default by these managed Kubernetes systems. So let's look a bit about the different systems. There's no surprise in there that AWS has a system called EKS, or what they call the Elastic Kubernetes Service. On Azure, it's the same but called different. There they call it the Azure Kubernetes Service. Google Cloud calls it GKE, or the Google Kubernetes Engine. And DigitalOcean has recently also launched one. They call it DigitalOcean Kubernetes. But there are many, many more out there. So you have a lot of different choices for a lot of different possibilities to manage, to use managed Kubernetes. So there is not one solution that is the perfect. As ourselves, as amazee.io, we use a combination of them. So make sure that if you look into them, research them, test them out. A lot of them even have free trials or very cheap ways of running just a demo cluster, and make sure, because even all of them say they do managed Kubernetes, the understanding around what managed means can be slightly different for each of these offerings out there. So with that, we are the first part. We talked about managed Kubernetes. Bastian, do we already have some questions?
We do not have any questions yet.
All right, cool, no problem. So we're going to continue, and if you have any questions, just throw them into the Q&A section in Zoom, or of course we can also answer things at the end. All right, so now we know how we can run a Kubernetes. We can either run it self-managed, or we can run it with a managed Kubernetes solution. Now, as the second part of this 102 webinar, we want to talk about the ways of deploying into Kubernetes, because just having a Kubernetes cluster itself is probably not the best. We want to actually run applications in there. And that being said, I want to make sure that there is a lot of change in this area right now. So what we're talking about today might not be true anymore in a couple of months. And Kubernetes is actively developed, and there's a lot of changes, but this is like a snapshot as of October 2019, and the different ways that we can deploy into Kubernetes. We're going to talk about four main things: that's kubectl, Helm, operators, and Lagoon itself. And we're also going to shortly look into a slightly bit more ways there are. So the first one is kubectl. Kubectl is the actual CLI tool that you can use on your computer to interact with the Kubernetes API. It makes it easier than actively using the REST API, but instead you have a small CLI that makes a lot of things easier. If you want to use kubectl, and that was for a long time, at the beginning was the only way to deploy into Kubernetes, you basically need to write YAML files for different Kubernetes objects, like deployments, services, ingresses. In Kubernetes 101, we talked about them, how they work and stuff like that, but you need to write them manually. And then you apply them into the cluster with kubectl create. And kubectl will parse the YAML files and send them to the cluster, and will create all the objects. But that's it. That's all kubectl does for you. And there's no version control. So you cannot go a version back if you want. There's also no rollbacks. That if something goes wrong, kubectl does not automatically go back to an older version. It also does not build any Docker files. So if you want to have custom images, which you most probably have, you need to build them before. You need to push them to a registry somewhere by yourself. And then in kubectl, you just reference the images. So it's a very raw, very rough way, but it's probably the closest one to understand how everything works. We ourselves use that quite often, but we mostly use it for testing. If we have a new system that we want to set up, if you want to change something in there or just test something real short, kubectl is perfect for it, but definitely not for any production workloads, because like mentioned, it can get quite hairy if you want to go back and figure out what exactly happened. Kubectl doesn't really provide you this. So as said, kubectl was the beginning that existed in the Kubernetes sphere, how to interact with the cluster. And then over time, another tool came into play, which is called Helm. Helm is basically a YAML templating language, which allows you to write these YAML files. You can write them with templates. So you have possibilities of injecting variables, to if-else statements, things like that, that allow you to change the templates depending on specific things. This means it's way more flexible than kubectl, where you have to write your own YAML files every single time. And Helm also does a lot about the version control. So Helm, for example, can do rollbacks for you. If you deploy something and it didn't go well, you can tell Helm, hey, please go back to the version before, which obviously is quite necessary in some specific cases. It does, though, not build your Docker files. That's still something that you need to do yourself. You need to push the files somewhere, and so Helm is not handling this. Plus, there is the understanding of charts. So Helm charts are basically predefined YAML templates for services. And because Helm now exists since quite some time, you find Helm charts for a lot of different services. So you have things like MySQL, Redis, PHP, Drupal, whatever you want to run inside Kubernetes, I'm pretty sure you will find somebody has written already Helm charts for it. And these Helm charts can sometimes be quite complex and with multiple services deployed at the same time and things like that. So there is a lot of possibilities that you can use with Helm. The problem though is that Helm version 2, which is the current stable version, is not really made for multi-tenancy clusters, meaning that if you have multiple people needing to deploy into the same cluster, but they should not really be able to see each other's code. With Helm 2, this is quite hard to achieve because it was just not really built for it. So there are workarounds around this, but Helm 3 is actually a full rewrite of this and will solve a lot of these issues. So about Helm, we can definitely see that it's right now most commonly used. It has some issues around the version 2 that you should read on and you should test and you should learn how to use them. But version 3 is very promising and already has reached the beta stage. So we hope that it's going to be out very soon, and then we'll see how much it can be used. Now let's talk about the future. So operators are basically the newer method of deploying into Kubernetes clusters. Essentially, instead of having your local computer just sending YAML files to the Kubernetes cluster, like it happens with kubectl and with Helm, operators are an actual application that runs inside Kubernetes. So these operators are built either in Go or Ansible or something else, and that manage another application that is also running in the cluster. You might say, like, why isn't that a bit over-engineered? Sounds like it in the beginning, correct? But because this is an actual application that runs inside the Kubernetes, it is able to coordinate a lot of things. So we can, for example, make sure that specific services are upgraded in a specific way. You can do rollbacks. You can do a lot of security. You can do statuses. So because it's an actual application in there, it's much more flexible and able to do specific workflows and things like that. You still need to build the Docker images. Operators do not solve that problem at all. So Docker images still need to be built and pushed somewhere before. But there is a growing amount of operators. There is the Operator Hub, which is the place that you can find if your service has an operator already existing, and more slowly there are more operators existing. So overall, we can definitely see that operators most probably will be the future of how we deploy into Kubernetes clusters. And many people are working on building operators currently. There's also inside the Drupal community, for example, there is a lot of talks about having a Drupal operator or a CMS operator, because we just see that these applications need more possibilities than just a YAML file that you throw once at the cluster, and operators themselves are solving that problem. And then the last one we want to talk about how to deploy into Kubernetes is Lagoon, our own tool. How does that fit all in there? So Lagoon is a fully integrated, not only deploying system, but also a building system. Basically, this means Lagoon is connected to your Git repository, and every time you deploy, or every time you push a new branch and pull request, Lagoon will automatically trigger a new deployment. While the other three tools that we saw so far, it always needs something locally to be triggered, and Lagoon automatically is triggered every time that you push into the Git. Lagoon also will build your Docker images based on Docker files. So that's one cool system that you don't have to worry about building these images. Lagoon does it automatically for you. And Lagoon provides a lot of additional functionalities on top. So you can do rollbacks. We can do blue-green deployments. We have possibility of version control. So you can go back if you need to know what ran before. There's a UI, there's integrations into Slack notifications, all kind of stuff. So Lagoon itself definitely needs some setup and configuration. It's not just something that you shortly install in your cluster. It needs a bit understanding, but it is definitely geared towards developers that just want to use Kubernetes as their deployment system. They don't want to worry about YAMLs and charts and operators and whatever. They just want to build their application and want to get them deployed into the cluster. There is what Lagoon comes in and helps out with doing all these things. And then, like it is in the world of open source, there is many, many more systems. There's tools called like Draft. There's a thing like GitCube. There is Casenet. There is Compose. There is Scaffold. So there is a lot of different ways how you can deploy your application into Kubernetes clusters. And we definitely suggest you to do some research. Each of these tools have their reason for existence. They do things slightly different because Kubernetes is a very new system. There are right now a lot of different understandings of how systems should be used. So we definitely suggest everybody that thinks about running their own Kubernetes cluster to use, to do their research. Or of course, if you're interested to deploy into Kubernetes, we're here to help. But if you want to do it by yourself, if you want to go that and do that journey, do your research, test the different tools, and make sure that they work for exactly what you use, what you need them for. Over to Bastian.
Yes, sadly, no questions yet. You can always ask questions. I'll answer them sometimes directly, and if it's a question that we can discuss in full, we will basically do a Q&A together with Michael. But back to you, Michael.
Cool, thank you. All right, we're already at the third part, and this is coming from last webinar. One of the questions at the end is, okay, but how does a cluster actually look like in production? So what we're going to show you now is a bit of a sneak peek in how we at amazee run our Kubernetes clusters in production. And this is obviously highly opinionated based on our experience, but we do this now since quite some time. So I would say that how we run it definitely is proven that it can work. But of course, there is definitely a lot of different ways. So this is a short overview of how our clusters are set up. And we're going to go from top to bottom and look into how these things are working. So at the very top, we have a load balancer, and these are usually load balancers provided by the infrastructure provider. So in AWS, it's an Elastic load balancer. Google Cloud has similar solutions, and we use them because they are usually the best way in terms of scaling. They are auto-scaled. You don't have to worry about scaling your load balancers. There's also much better security. A lot of times they have DDoS protection and things like that. So we leverage these with either fixed IP addresses or not, depending on the infrastructure, but that's usually provided by the infrastructure provider. And then we have a list of load balancers or reverse proxies. So these are Kubernetes nodes that are running the different ingresses. So in our case, we have an HA proxy running, other people use Nginx, it doesn't really matter, but this is where every single request, the load balancer just forwards the request to one of these three reverse proxies. And there, they then actually know, like we learned the last time, to which pods should the traffic be forwarded. Also, the thing that happens here is SSL offloading. So the SSL is terminated here. And we use things like Let's Encrypt, for example, to automatically generate SSL certificates. But that's where the SSL offloading happens, and the traffic after that here is usually not encrypted or sometimes re-encrypted depending on the needs, but the SSL offloading happens over here. Technically, it will be possible to just use regular compute nodes for this, but we decided to have dedicated nodes that are only doing that reverse proxy. Reason for that is that because of that, we can usually scale these nodes a bit smaller, but they are only running usually 2 or 3 pods on them. That's the proxy itself, and then obviously some management and monitoring things, but they are dedicated for that. They are not getting any production load, so they are dedicated for this. We use 3 of them because usually we deploy into 3 different, in AWS terms, availability zones. So that means these 3 are running in different availability zones. So if one of them has a problem, there are still 2 that take over, and there's also not needed much like scaling, because these load balancers, they're pretty performant, and that's how they stay there. Then going further down, we go into compute nodes, and the compute nodes is where the actual applications are running. We can also see that there is a server 3+. This means that's also where the scaling happens. So if the Kubernetes cluster realizes that we need more resources, and what happens is that Kubernetes automatically starts additional compute nodes and adds them to the cluster. The reverse proxies will automatically see that and send traffic to them. But that's where the real processing happens. These are usually quite big nodes, and they usually have like 16 CPUs, 30 to 60 gigabytes of RAM, and then this is where the actual computing and your application is running, and that's where the scaling happens. Again, this is usually deployed in 3 different availability zones or regions, to make sure that if we lose an availability zone, there is others that automatically can take over, and to generate high availability possibilities. So up until here, this is probably like a regular cluster, but as applications, they need persistent storage. So, and if we talk about persistent storage, it's actually usually 3 different types of storage. Sometimes applications need just block storage. So that would be, in AWS terms, your EBS volume. It is possible for Kubernetes to automatically provision that block storage and attach it to a pod or to a container if the pod requires it. But there is also file storage. So these are things like NFS, or where you just want to store some files. And then the third one is object storage. So that could be things like S3 and the other type, where you just have some objects that you want to save. And all of these 3 storages, we all use them. So it's not possible to just focus on only one, because depending on the application and the needs, you have different storage needs. All of them, though, are managed by Kubernetes itself. So whenever an application comes in and says, I need some file storage, Kubernetes automatically talks to the infrastructure APIs and gets that storage, provisions it, and attaches it to the pod. So it's not something that we manually every time go in there, but it's automatically attached. But of course, you need to worry about this. You need to make sure that all of this works. And there are some caveats around how many, for example, block storage can be attached to a node. Block storage usually cannot be attached to 2 nodes at the same time, while file and object storage, that's possible. So there is a couple of things that needs to be figured out, and for each of the services, needs to be seen what exactly is necessary. So that's about persistent storage. And then we go into databases. Now, databases are always a big discussion around, because you technically could also run, let's say, your MySQL inside the pod, inside the compute nodes. Now, while this is possible, it's probably not the most performant and most efficient way. First of all, because just running one single MySQL pod inside the compute node, if that MySQL pod or any other database has a problem and needs to restart or needs to start on another node, because these databases, they are stateful. This means they have a state. They need to first stop themselves and then start on another level, on another node. And during that stopping and starting, your application is most probably not be reachable because it cannot talk to its database. And specifically, Drupal is quite bad. It cannot function at all if the database is not working. And then, of course, there's a possibility to actually run a MySQL cluster, so something like MariaDB Galera, inside pods themselves. But again, managing all of this and handling all of this can get quite hairy and quite complicated and very fast. So what we now do today is that we deploy a dedicated MySQL cluster if the infrastructure provider provide something like this, let's say RDS at AWS or in other environments, we use them, or we also have systems where the infrastructure provider has not a MySQL cluster and we just run our own Galera clusters in there, but we do them separate. And like it works for the storage, and whenever the application comes up and says, I need some MySQL, what happens is that the Kubernetes itself talks to the SQL cluster, creates a new user, a random database, and injects these information into the pods running on these compute nodes as environment variables. And then the application, for example, Drupal or Symfony or Laravel or WordPress, then use these environment variables to then talk to the databases. And the database itself is a MySQL cluster that is multi-availability zone. So it's an HA system, it's backed up, it has read and write. So it's all what you would expect from a MySQL cluster in there as well. And the applications just use it. Of course, it's possible to have multiple MySQL clusters, and we have this in many cases. We have like development and production ones, but sometimes we also have dedicated ones for one customer. They get their own cluster. So depending on what is necessary, we change these things. And this is also the case for any other databases. Of course, MySQL is not the only one. You maybe have Postgres, you need Elasticsearch, we have Solr, and all kind of other systems that want also some databases. And usually what we do today is we create a dedicated cluster for them, and then the compute nodes talk to that clusters over there and not actually deploy themselves. All of that is very actively deployed or worked on. Like right now, we still have Elasticsearch in there, but we're working on a system that can do a separate cluster. So that's where really the work happens. Most of it is figuring out what is the best way to run these applications and work on them. So this is basically our cluster, and that allows us to deploy pretty much any application into the system. But beside of that, like we learned before, that itself is not it. First of all, you need a control plane. Now, in our cases, we usually use some kind of managed systems if it exists. We have situations where we run into infrastructures where there is no managed Kubernetes existing. So therefore, then we run our own. But if it is there, we like to use it. And then we need to worry about backups. And with backups, we use a tool called KUp. K8up, however you want to say that. It's basically a Kubernetes native system that automatically does backups and stores them for you. You can do restores. It's a really nice Kubernetes native system to do backups. And then we need some monitoring and alerting. And there the gold standard is Prometheus and Grafana, which basically Prometheus is running inside the cluster, understands about all the different pods, the services and that stuff. And then, of course, Prometheus also monitors the MySQL clusters, any other databases, file storage. We use Grafana for showing the different, to have graphs and stuff like that, and then alerting with Alert Manager. Plus, one thing that we use Elasticsearch for is all the logging. So every single pod creates logs. These reverse proxies, they create logs, the load balancers create logs, they all end up in an Elasticsearch, which then with Kibana can be accessed, and the different logs can be viewed and seen and analyzed, and yeah. So this is basically how we run Kubernetes in production as of today. You can see it's quite easy. It gets quite complicated, and it's not just using managed Kubernetes and starting that and running it. For testing purpose, definitely that's possible. But if you want to run it in production, you need to add a bit more than just having a managed Kubernetes. We, from our side, definitely suggest everybody to play with it, to try with it, but be aware what it means to run things in production. And if you really want to start, we definitely suggest to maybe talk to somebody like amazee, but there's also other companies out there that do the same, that can help you with actually running your own Kubernetes cluster. from our side as amazee, if we start a cluster for somebody, a dedicated one, all our customers get full access to everything, so they can see how we run everything. They can see, they have access to the cluster, they have cluster admin if they want, so they can see what we do and also learn from there, and maybe over time do it themselves. But just jumping into the cold water with never running Kubernetes in production, it's going to be an interesting journey if you want to do this. All right. That's it for today. Do we have any questions, Basti?
We had one question about scaling databases, but I think we already basically answered that in full in your explanation, and we don't have any other questions.
Cool, yes. I'm shortly reading the questions. How is scaling? Yeah. It's definitely, we went through the journey of initially we ran the databases as pods on these compute nodes. And then over time, we realized that it's probably a better way. It's a more sane way to run them in dedicated databases. That being said, that might change in the future. Obviously, a lot of database providers are now improving their own systems. So they are more container native or more serverless native. And so this might change over time how we run databases. But as of today, I think the best way is to run the databases outside of the actual pods. It's just going to make a lot of things much easier. Cool. I think with that, we can finish this webinar for today. Thanks everybody for joining.
Thank you.
And Philip, I think the videos will be sent around.
Exactly, yeah. Thank you to the two of you as well for leading us through the presentation, and again to the audience for listening in, dialing in, calling in from all of the various locations. As per usual, we'll be sending a follow-up email with the recording of this entire presentation to your inbox within the next couple of days. So expect that one to come out. And another reminder, if you missed the Kubernetes 101, that will be in our blog, but we'll make sure to keep that one in the email to you so you have it both in one nice bundle. Excellent. Thank you very much again, and enjoy the rest of your day. Goodbye.
Thank you.
Thank
Bye,
you.
everybody.
Bye.